So there's some main thing I want to announce first. As probably you know, our class would have a tutorial, optional, which will be according to the TA. He set it to be next Tuesday, at 6:30 to, I don't know, 9:30. I don't know why 3 hours, but he will put it on the Zoom and also record it as well. So in case you don't have time, you can do it on Zoom or you can do it in person. I think it's in LSB. And then there will be another one that with other tutorial that at the end of the semester will be November 20th. And also he will review the chapter 4 on work. So basically you have two tutorial, both of them are record and also on Zoom, so you can attend online or you can review later. Basically reviewing materials that are and also answering questions. So if you have questions, then feel free to email the TA, Zili. I mean, you have question to ask him, and then that'd be great because I guess this is we're lucky because this is we have extra TA compared to all other sections. We are lucky to have two TAs, but usually don't have tutorial for this one. But it's optional, so there's nothing new from here and from there, or if anything that you can take a look and have fun. And I haven't released that one yet. Quiz 4 will be released now, which I haven't do it. Let me do it now. Let me release to you at the moment. Make it available to you now. So quiz 4, it's there if you want to take a look on those. It will be concerning if you to see that you were talking about statistics and sampling distribution, the idea. So over time you can have fun, but as we said, this kind of quiz is just for attempt. So as long as submit, you get all the credit. I don't care whether you get right or wrong. Okay, we don't check. We just check whether you did or not. So make sure you did it before your final exam or the end of semester, which we count your whether you have done it. Okay. So sorry, I know already know my sound is not normal because I've been sick since Saturday. I mean, I'm taking rest these days, but still not fully recover. Hopefully my brain is still working a little bit. I mean, but I think it's okay. I mean, although this day my brain is a little bit foggy, but I think for this lecture I've been teaching for many years, so it shouldn't be a big issue for you. Still be fine. I guess it shouldn't be. We're not teaching anything wrong, I guess, right? I mean, if anything wrong, let me know. So I think we're done with the sampling distribution. We are going to touch off on the estimation, and we will not likely finish the whole chapter. Maybe leave some, maybe up to sample size today. So up to slide 44. Okay, so that's the goal. So what we have done in the last week, right, would be sampling distribution, right? Just to quickly remind you what we have done. This is the first chapter. We take data seriously, and by taking data seriously means that we have to consider how we get the data. And often we get data is not we will do it through a random process, right? Just like because who you talk to is not known in advance, right? If you know in advance, we don't have to do things, right? So that's why probability will be the main thing here, right? Because it depends on which individual you talk to in the population that you're interested in, right? And very often it's very important to get a random sample instead of you do the sample, you know who you talk to in advance. You know the very advanced, right? Otherwise, if you are just fixing some person, then it probably you only get, of course, you get the person you want to look at, but the you can't really extend your knowledge from your data to the general picture you want to study, right? Because that would be something really depends on how you pick them in advance. So we know the population sample, and then we learn all the thing that from the sample are random variable, right? And statistics is the way that how you combine the things you get from the simple random sample, right? And then the example would be sample mean and sample variance. And sample mean is the adding all the observation over n, right? That is also a random variable. When it's a random variable, then it means that we can describe it, right? We have to describe it through the big P or big F or small f, right? And also, and big P and big F sometimes are difficult to look. Then you look at the expectation of variance, right? And the big P and big F we know is going to be collapsed when n is very large, right? That's for law of large number. The sample mean will be the population mean, and the central limit theorem said the big P and the big F looks like normal. Okay, so that's something we have already. And I guess last class we talked about the central limit theorem and the case of binary data, right? Also applies, but the mean and the variance are connected to each other. So that's why you have this kind of formulas. And at the very end, we talk about the case where the sigma is not known. Then you would have to assume the underlying population follow a normal distribution. Okay, and in that case, sample mean is also normal, and then we can apply the t distribution if we replace the sigma by sample variance or sample SD. So that would be the key that we have covered so far. And we basically learn what sample mean looks like, right, in this one. Of course, we didn't learn sample variance, but that would be a case. That would be, in general, we don't know, right? But if that will, if you learn that if you learn further, this is not I guess is I shouldn't talk too much on something you haven't learned, but so the next thing is about estimation, which is the topic of this week. So we'll finish this and on Friday, okay, as well. So the main thing is estimation is trying to extend or draw the knowledge from the data, okay, and our conclusion from data or the things we learn from data will be transmitted to the population. Of course, the things you want to learn from the population, of course, the best thing is to want to know the big P or the big F or small f, right? That was something we want to know. If that is possible, because if once we know that, then we know everything, right? You know the distribution, then we know everything we want to know. But the fact that that is too ambitious, at least for our skills that we have. So the easiest thing to do is to try to understand the basic thing, which is the mean and variance. Okay, so of course, if you want to more than that, you want to know kurtosis and skewness. That is also available there, right? We know the formula there, but we don't have time to discuss. And the thing you learn in topic 1 about the skewness and kurtosis is also valid. Okay, but in this class, we just show you that why the sample mean is good for the population mean and sample variance is good for population variance. Okay, we'll talk about unbiasedness and this kind of idea. Okay, so this is something we want to know about the population, something we want to study. Okay, And estimator is the way that you use the data to estimate, right? So if you look at the definition here, in this, the first part, this is definition of statistics, if you remember. Okay. So estimator basically is a statistics to estimate parameter. So it's a way or the rule, it's a systematic way to estimate the population parameter. Okay. So sample mean, right, is a way to estimate population mean. Sample variance is the way to estimate population variance. And since statistic is a random variable, right? So estimator is also a random variable. The reason is it really depends on which individual you pick up from the population, right? So that is something that have to be very careful. And once we get the data, then when you calculate that, they become estimate. Once you calculate, it's no longer a random variable. That's very important because once a number, then you no longer can assign probability. Okay, it will be very clear at the second half of this class why we have confidence interval, not probability interval, because of we can't say probability, and you have to be very careful about this. Okay, and not how to say it because probability can only be assigned things happen to happen. If things have happened, then you can't say probability. Okay, at least in the classical way. And we're in the classical class, so that's why we have to be very careful. So I guess we know very well what are the two types of estimator. One is point, one is interval. Point estimator is simply that number you're going to give, right? And that's the best guess we want to have. But interval estimator is not just a number, but rather we want to give a bunch of number, not one. Maybe you give the lowest, most conservative, and most aggressive. The best case or the worst case scenario, right? It's like more than one scenario. So you give interval estimate. Okay. So to convince you that this is the case, and then actually you often seen then not just here is you look at the, I think it's good to look at the observatory. So let's see the images. So this is, but although this is Macau, I think that's fine. Let me use the Macau one. How can I visit this diagram? So sorry for those who don't read Chinese, but this is typhoon. I think that like 4 years ago. Then you can see the typhoon is here, and it will pass through here, and then you can see the yellow and the blue. So what's the blue here? Blue is the point estimate. That's the best guess among they have. And yellow is called interval estimate because you are not guessing one point, a bunch of points. And I guess this doesn't show it properly. Let's figure out another graph. So this is better. I think this is Hong Kong version. Let's see. Can I double click view image? Yes. So this will be the image, right? You will see it assigns some probability. Of course, there's some issue about probability anyway. But anyway, let's assume this is fine. So do we see there's a 90%, right? It's here, right? And then the more blue color, that's less likely, right? So you would often not just want to give particular estimate, but you got give a range of number that you would guess. Okay, and that is the reason why we have point estimator and interval estimator, right? A point give you a point, an interval to give you a bunch of number, right? And then you may ask, okay, why this is not a point, right? But this is just every single of this is point by each time, right? So still we still get a point even though a line is given because you're choosing a path over time. And very often you look at the news, especially financial news at the morning, right? There's a expert who asks to guess what would be today's stock index, and you've given a number. Usually, you give a number that would be point estimate, right? And they also give a max and a mean, the highest and lowest. That will be called interval estimate, right? They will say it fluctuates between 26,000 to 28,000, right? And you also say it will likely to be 27,000, right? So that's a point estimate. Now, we first focus on point estimator, and we will try to convince you that our sample mean and sample variance are good estimator. Okay? And you will see why our sample variance is divided by n minus 1, not divided by n. And although we don't cover it, but you can expect the reason that we have the sample kurtosis and sample skewness are such a funny formula. Okay, there's some reason that behind, that will be here. Okay, so there are many good properties of point estimate that we don't have, and these are the three. And this is you can find in a textbook. Every textbook would put this thing out, and we will do it one by one. Unbiasedness is a very weak requirement. It only requires you on average hitting the target. So you don't have to hit the target, but on average hitting the target. So that would be the idea. So imagine that you are an archer and you want to hit the bullseye, which is theta in the middle, but you don't really hit on it, but you can on average hit on it. There's unbiasedness. Okay, I think I give this example again, right? Let me say it again, right? So there's a football goal here, right? And there's your favorite football star, maybe Messi or Cristiano Ronaldo, right? Then they're so good that they are able to kick in almost the same point, right? So these are blue are maybe Messi, right? Maybe Cristiano Ronaldo, something similar. I don't know. Maybe something like similar, right? So, but on average, they're hitting the target. We're close. Okay. Maybe this is right. Cristiano Ronaldo, right? Messi is blue, right? Because he's from Argentina. And maybe here is another guy, me, right? Very bad football player. So I'm very bad. I'm unable to get the ball in the goal anyway, but I'm good enough to be hitting the ball here, here, and here, right? Not very good, but you can see on average, I'm hitting target, right? Although I miss on every round. But in terms of unbiasedness, three of us the same. So I'm as good as the other football star in terms of unbiasedness. Okay, unbiased don't have to be good, but it just means on average is good. Okay, so that is very weak requirement. But if this requirement doesn't satisfy, then it's very bad. Why? Because if we are to expect ourselves to repeat the sampling many times, we get many feet ahead, right? Then we want the average of the feet ahead, we recover our truth. If not, then it's not very desirable, right? Of course, there's some reason why this is not must, but it is good to expect this is something we want to have, right? Just imagine a science, right? A lab do something, and a lab do something, and a lab do something. You want the average outcome of this lab actually recover the truth. That is the meaning of unbiasedness. Okay, it doesn't matter how good it is, but on average, at the end, we get what we want. It's called unbiased. Okay, means that without bias. And of course, you will say it's crazy because you will say I am same as all the football star, right? So how can you distinguish me from the football star, right? At the end of the day, right, they earn millions or billions of dollars, right? I'm earning a very low salary compared to them, right? So why is the case? But it's easy to see that it will be what I call efficiency, right? I have much higher variance than them, right? And you can imagine the graph is like this. So A and B on average is hitting target, so they are both unbiased. And given the unbiased, and then you can see A on average is closer to the mean compared to B, right? So variance, remember that the meaning is look at this distance, you square, right? So this for A, and you compare to this B, the distance, right? You square them, okay? And you can see that the distance for B, you square, right? It will be much larger than A. So on average, B is not good compared to A. Okay, we'll say A is more efficient than B. Okay, and in that case, we'll say Macy or CR7 is more efficient than me, right? Although we are unbiased, all of us unbiased, but they are more efficient than I, right? So that's important. Right? You want to pick the unbiased and efficient, right? Because you want to pick on average is right, and yes, smaller variation, right? Because the closer to the target, right, is more accurate. Okay, so the last one, of course, is something that the third one is even more important. Is we expect this to happen is the variance should shrink to zero if n go to infinity. So the variance in the short run means should go to zero, right? So that is, but of course, that the formal definition is above. So one of the implication is you should things should shrink to zero. So you, in the end, if you increase the sample size as large as you want, it should get what we want, right? So that is something we want to see, right? So that's the graph is like here. When the sample size is 1 or small, it will be outside. When 2 is more inside, 3 is further inside. So you increase sample size will get, eventually you will be there, okay? So that is a consistent estimator, means when you get a larger and larger sample size, okay, it will be very, very close to the target we want, okay? That is the idea. Of course, this need not be unbiased. Okay? Can be biased estimator, but consistent only saying at the limit, when n is getting very large, you'll be there. And any finite n can be biased. Okay? Of course, at finite and infinite is still, you will not be unbiased, right? Because they're exactly the same. But they simply say in terms of definition, one of the implication is the variance will shrink to zero. Okay. So in the case of sample mean, this is just the law of large number. The law of large number said, right? The sample mean will be population mean, right? So that is the idea. Okay. So these three properties very important. So and that's actually sample mean satisfy all of them. Okay. Actually learn that unbiasedness is come from the last chapter, right? It doesn't rely on anything, right? The second one is efficient. Okay, efficient means that the variance smallest. Okay, and what you compare is you can compare sample mean with any other weighted mean. Okay, and I don't want to spend time. But sample mean is the most efficient compared to any other weighted mean. Okay. And the last one is come from, as we said, consistency is from law of large number, which tells you that sample mean will approach to the population mean when n is very large. So this is more or less to explain why we've been using sample mean. Okay, it's a good one. Is that okay? I think we have studied that already. So probably we are now resolved the mystery at the beginning of our course when we say sample variance, why we have divided n minus 1 instead of n. Okay. So, of course, the easiest reason is because this is unbiasedness. So because of this. Right? So that is, which we will show, is this guy. Okay, we will show this is true. Of course, we don't have time to show you in the class. You can check the proof. I think it's 4 slides of proof. I think it's like 15 equations you have to solve. You have to go over. And those of you who don't like math can forget about it. Okay. But I can tell you the intuition why there's the case. Okay. The intuition is actually not that difficult. The main reason, actually, if you go over the proof, because of this guy, X bar. If we know the mu, okay, we place a mu. We don't need to do n minus 1. If we know the mu, and we only need to estimate sigma square, we just need to divide by n. The reason that we need to divide it by n minus 1 is because we don't know mu. And we have to estimate mu by X bar. Why estimate X bar would need us to divide n minus 1? That's a question, right? Of course, if you go to proof, then you will see. But let me give you the reason, and this is the reason that you find in many textbooks, and I'll always find very confusing. And hopefully, the way I explain would able to convince you this is true. So the reason is the following. You estimate what is S square estimate. It's variation in the data, right? That's the meaning. But when you have to estimate X bar instead of using mu, actually the variation is less than what you think. Why is the case? If you have estimate X bar, and if you know the first n minus 1 data, you know the data but the last one. The last one has no variation. Why? Because I fix the sample mean. I know the first n minus 1 data. The last data, there's no variation. Because adding up all the data divided by n must be the sample mean. So the last number has no variation if you have to estimate X bar, right? So the variation has only n minus 1. So that is the reason. Okay? It looks like magic. Okay? I've told you that I told you I never understand. When I was a student, it took me quite a while. I look at the library, I look at all the books what I can find in those days, 10 years ago, and I still don't get it, to be honest. I mean, they said, oh, this is degree of freedom. And that's it. I mean, that is what they told me the story is like, okay, you estimate, you have estimate one more parameter, then you lose 1 degree of freedom, and that's it. But what's degree of freedom? Okay. It's not something that I would grab it, okay? But you look at the math, that is due to you have to estimate X bar. And X bar is not something that is coming from the data or also as well. So by doing this, you actually have less variation than you think. Okay. So but now I get it, because look at the math. It's just like, because if you actually have mu, you don't have to do that. So now I understand, okay, that is the main reason, because of if you know mu, you don't have to you can divide by n. That's the right one. But you have to estimate mu by x bar. You actually don't have much variation as you think, right? Because of once you estimate that, the last data point is already fixed. Something has been fixed. So you don't have a lot of freedom as you would want to have. So that's the reason. But but I would say you will not easy to get why this is true. If the first time for you to see it and you don't want to go for the proof, then you can just take it as by faith. Okay, is you have to trust it. So there's nothing I can say. There's nothing I can convince you, except the fact that there's a 1 page of proof, 2 page and 3 page. You can just try to see why that's the case. But as I explained, that is due to the fact that you estimate that guy. Otherwise, you don't have that, you don't have this problem. But just take it as given. I don't want to say anything, but already I explained why that's the case. There's some intuition in the slide 22, but if you want to read it, you can read, but I'm not going to go over that. And actually, degree of freedom actually is something to be true for many general case is when you estimate more stuff, your degree of freedom, which means that the variation actually reduce. And then when you estimate this variation actually will reduce n-1, and then when you learn multiple regression, you will do n-2. That is what happened when we go to the end of the semester, we say regression, because we estimate the slope intercept. Then when you estimate the variation of your data, then you will be n-2. Okay. So I will explain it with this when I come to that class. So the next is standard error of the mean, which is just S over root n is replaced by this. Is remember the standard deviation of the sample mean, so it's replaced. And the binary data is just special case, right? So sample proportion is unbiased estimator of the population proportion. That is nothing new there. But you will notice that when we use the binary data for the population variance, we still just use this one. Okay. We don't have n-1. You may ask why, right? And this is a bias estimator. It's a bias. Because the thing that if you follow the same procedure, you should see this guy is as an unbiased estimate. Okay. The reason for this is this guy will be very close to zero anyway. Because when you do binary data, n is very large, usually 100, right? You cannot be, then this guy will be basically close to 1. So don't really adjust, doesn't really matter. But then doing so, you simplify our formula a lot. Okay. So that's why we didn't do it. Okay. It's a bias, but we just do what people are doing. Okay. I'm not going to challenge it well. This is, you can see the standard textbook, they just replace this. So that is what we would do when we talk about interval estimate. Okay. Is that okay? The only reason why doing this is because we can estimate pi, okay? And that's why we just replace by this as a way to estimate. Okay, because this is pi. P is unbiased estimator for pi, so we just use this formula to do it. Okay, but this is not an unbiased estimator for the sigma square. So we have to, but there is some reason why we do this, but that should be okay. Okay, for the moment, that's what we're doing. Okay, so there's a formula there. So there's no question. I will just give you a very brief overview on the interval estimator that we can talk more after the break. So one thing we know that X bar, the sample mean, is a good point estimator, right? So suppose someone want to ask you what is the average willingness to pay for your new product, right? That is, you want to know the mu, then of course the easiest thing is to X bar is a good, right? You look at data, you look at sample study, you come up with X bar, that's a good estimator for the mu. But you want to know how good it is, right? So that is the reason why instead of estimating the point, you want to come up with how good they are, right? Then the easiest thing to do it is you have to know the distribution of X bar, right? That would tell us how good the estimator it is. And if we invoke normality or central limit theorem, we know X bar follow normal distribution, right? With mean mu sigma square over n, right? So that would be something we can utilize this, okay? To extend our knowledge is how good is our guess, right? So that would be the main thing. It's like, this is good, but how good is it? Can we extend more? Okay. The main idea is to do the following. So it's very important. So make sure that you get this point. So what we're doing is we're going to have a symmetric interval over X bar such that we have high probability to include mu. What do I say? Okay. First, mu is not a random variable. Mu is a population parameter. It's a number. The population mean is not a random variable, right? So this is mu. The example would be how much on average people want to pay for a product, which is not a random variable, right? You just don't know it. It's not a random variable. What is the random variable here is your X bar, right? Because it depends on data. It depends on who you talk to. This is a random variable. So what we want is I want my sample, if to be done, okay, then I see if the pen is not useful. X bar, right? Once I have this, I want to go left and go right, okay, symmetric. So I go left and right by M, right? Or ME. So X bar, there will be X bar plus M here, right? This is X bar minus M here. Okay. I want this interval. Okay, this interval is random, remember, right? Because X bar is random. And I want this interval have 1 minus alpha probability, which is high. Alpha is usually set to be 0.1, 0.05, or 0.01, right? This is a small number. We have high probability that this interval will include mu. Okay. Let me repeat. Mu is a number. You just don't know. There's no probability. The probability you can assign is X bar, which is sample mean, because the sample mean depends on the sample you draw. It's a random variable. There's some probability. Okay. And what we want is we want the sample mean to go left by M and go right by M, which is M is called the marginal error symmetrically. Is this will have high probability that will include our population mean, which is something we want to guess, right? So that is the goal of it, right? Is that clear? So let me repeat, is we want, once we guess the sample mean, we want to go left and right by the same distance so that you will catch our population mean. Okay, population mean is a fixed number. We don't know where it is. Okay, but we want our guess have high probability of including it. Okay, so don't worry, we will go into detail after the break. So if don't have any question, let's have a 15 minutes break. As usual, we'll do our U reply. So see you in 15 minutes time. assignment 俾 plan 噶嘛。assignment 交咗就得，即係 assignment 等於哦。係啊，一樣㗎，兩個唔一樣㗎，兩個唔一樣。咁啊，點解唔一樣？個口上兩個唔一樣嘢嚟，但係同一樣嘢嚟，七個呢樣嘢，將7個雞蛋擺喺7個籃，7個雞蛋擺喺7個籃，我哋唔係可以7個雞蛋擺，我哋好緊要。small part of our side。我呢個我話俾你，呢一題係基本上大個人都接收。佢如果係我覺得有7個雞蛋係放喺同一個籃度嘅，7個籃度嘅籃雞蛋。單尾嗰啲嘢啦，或者放到邊嗰啲嘢，真係其實咪最難覺得都難嘅，都比較難，基本靠唔成。對，我就係呢個，對呢個。 So let us slowly resume. Do I mind to explain n-1 again? So yes, let me do it. So why n-1? Okay. The main reason is you would divide by n if we don't have to estimate x bar, which is mu. If we know the mu, the old formula we have would be fine. That's absolutely no problem. The problem, as you will see the proof, if you ever try to look at it, is because we estimate x bar. By estimate x bar, actually your variation of your data was less, right? Because we want this sample variance to guess what's the variation in the population, right? What is S bar, right? What is S, right? Remember what you're doing, just to remind you what you're doing. This is the population, right? There's some data point here. Data point here, 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 right? So what you're going to do is you want to use this, the data estimation S square to estimate the overall variation of the data, right? So if you know the mu, okay, that's no problem. The variation of this should be variation of this, right? Because you have variation here. So why you have n-1? It is because of the thing you have to estimate x bar. Once x bar means what? If I have first two observations, the last observation has been fixed. Why? Because 3 of them add up divided by 3 must be x bar. So you don't have 3 variation. You don't have 2 variation, right? Because once I fix the first 2, the last one has been fixed. So the number of variation is not 3, only 2. So that's why you can only divide by n-1. That's the reason. Of course, the real reason is you have to go to the math, right? I don't want to bother with you with that, but that was the math to show you that it is actually n-1, right? But the main idea is because you estimate this, right? So you calculate the variation is this square plus this square, right? This what is mean by this, right? This is you estimate by this square, this distance square over by n-1. Why? Because actually you don't have 3 variation. You only have 2, right? Because of once I know this, I know the first 2, the last one already been there. So that is the reason they call degree of freedom is reduced by 1. Okay. Of course, you really want to go to the math to see why that's true. But the math is like this. A lot of line because of this, and then you all do the calculation and turn out to be like this. But I don't want to bother with the math. You are getting lost after the midterm and your focus. I can understand. And another reason is because we're getting more difficult in terms of theory, because now we're getting more abstract, right? Before we're having before we're very concrete talking about distribution, but now we're talking about data. You have to imagine who you talk to, right? So that is always the case. Is a lot of people actually getting lost from the second half of a semester, and I think it's also similar to many other classes because you kind of burn out a little bit. So that's why you can see I'm slowing down a little bit. But if you have a question, again, please feel free to leave message here. I can explain. Or you schedule appointment with TA. There's also. Third, for those of you who arrive late, we actually do have a optional tutorial. I think it's next Tuesday at nighttime for 3 hours. And it will be on Zoom, also record as well. So you can attend those. And you're welcome to send your questions to the TA so that you can answer what you don't know. Okay, so this highly recommend, but of course, there is a standard TA, and also me, you can also ask question. A bit cold, yeah, that's true. Yeah, need to check it. Yes, we will go through the start of interval estimator because we haven't done yet. Okay, we'll do that. Yeah, it's Wednesday. Yes, rainy and cloudy. Yes, I don't think it's sunny, but pond estimator, typhoon estimation. Yeah, yeah. Population mean is not it's a parameter. It's a number. It's not random variable. So I think I'm losing some of you because usually I don't see one or two, but now I see some of you one or two. So I try to see if and so along we have many people are very tired. 2+ size ladies walk into the bar, order drink. The bartender noticed the accent, asked, "Are you ladies from England?" Outraged and mistaken. Wales. I'm sorry. Are you two Wales from? Mm-hmm. Midterm so much for me. Oh, I'm sorry about your midterm, but midterm do have some good benefit is because you're forced to study. And sometimes I'm thinking about getting midterm for a class so that you're forced to study. But I guess your life is so miserable, so I don't really want to add more burden to you. But you should try to do the quiz, which is kind of substitute of the midterm. So make you study a little bit. You know where you don't know. Otherwise, you have some problem. So worry not too much about the point estimator. I'm not interested in asking why they are true or why they're not, but just give you some idea why we are using this formula. So as long as you have this formula with you in the exam, so I don't see a big problem. It's open book exam, so I don't see it too much issue, right? Because I'm not asking the proof, right? So this shouldn't be an issue, but it's good to see why we're using them, right? And here is interval estimator, which we spend a lot of time on this, is for the rest of this class, will be answering what interval estimator is. Let me repeat what we are saying, because some of you asked me what is again. So the idea is the following. We're X bar, okay? And our goal is to estimate mu, right? And we know that this is a random variable, and this is not, this is a number. This is a fixed number, we just don't know. And this random variable, or what we call statistics, or what we call estimator, is a good to guess mu, right? That is what we know. Because y is unbiased, which means that we have many x bar, average of this x bar is mu. And it's also efficient, has very small variance, and is also consistent, which means that when we have large and larger sample size, x bar is exactly mu. But we also want to have not just this, right? We want to say a little bit further is because the probability that x bar is exactly mu will be 0, right? When n is finite, right? N is small. The probability that x bar equal to mu is 0, right? That is what we learned, right? It's called this random variable. What you get is not exact, right? You have many x bar, then of course average should be very close to mu, and also we have when the sample size is very large, is right. So what we want is we ask the following: can we go left and right by m, right? such that with x bar plus m and x bar minus m, okay, such that we have high probability that, okay, this will include the mu, okay? And we know from the central limit theorem, okay, or what we call normality assumption, that x bar will be centered mu, right? And with sigma square over root n will be its variance, right? How, when the bell curve is how fit it is, right? So what we want is the following. X bar is a random variable, right? Sometimes here, right? Suppose this is the data we got. We're here. We want go left by m. We go right by m. Okay. In this particular case, we're successful because this interval included population mean mu. Okay. Of course, this is not the only case. We can be somewhere here, right? We also go left by m and go right by m, right? So on and so forth. And of course, this realization, whether you get purple or orange, right? Or you have lucky, you are deep far away here, right? You go left by m and go right by m. In this case, this is not a successful case, it's not included. Okay. What we want is, we want the process we do, the m, right? We have high probability that this interval will include the mu. That is what we call interval estimator. Okay. Of course, not, you can't be every time because normal, right? So it can be, this x bar can be very large or can be very small. It's very far away from mu. We want the probability to be 1 minus alpha. Okay, alpha is very small, right? Alpha is like 0.1, 0.05, or 0.001. So which means that we have 90%, 95%, or 99%. This interval will include, right? That means that if I have 100 interval, 99 will include, or 95 will include, or 90 will include. So a lot, majority will include. So that is the main goal. Is that clear what we are doing? Right? Remember, the interval are random variable. Okay? And we want, if we get data, actually want most of this interval would include mu. So that is the idea. Okay? Remember, mu is something we don't know. Okay? And x bar are all the random variable. So the question is, how large is the m, right? If m is very large, then it's always true, right? M is very, we go left and right by infinity, of course, it includes everything, right? So what should be the m? So turn out, let's say simple logic here is, if you want x bar go left and right by m, okay, to include mu, it is equivalent to saying the following. It's same as your mu here. You go from the mu left and right by m. As long as the x bar is within this region, this is the same as what we said here. As long as probability is 1 minus alpha. Right? Because if x bar go left and right by m will be same as X bar is within this region, right? Because once they're within this region, you go left and right by M, of course it will include mu, right? So that's why we can just focus on mu plus minus M, then we're done. Is that clear? Because you include, you touch me or same as I touch you. So whether X bar touch mu is same as mu whether touch X bar. Same thing, right? You just reverse the idea here. There's something, nothing. Okay. So if I want the probability is alpha here, how can we calculate this M? The answer lies on this normal, right? So if you remember, if standardized normal, this is 0 here, right? 0 here. Okay. And if I want the inside is 1 minus alpha, right? 1 minus alpha. It's symmetric, right? So that means that these are alpha over 2, right? Because the both side alpha over 2 add up is alpha, the middle is 1 minus alpha, right? So we call this value Z alpha over 2. Okay? Z alpha 2. And remember what's this value? This value is, this means that how, if you convert this to the original normal, what is this number? This is, this distance will be Z alpha over 2 sigma over root n. Why? Because the variance is sigma squared over n, right? So the SD is sigma over root n, right? So we just, how many SD? We just Z alpha over 2 times of SD, right? Because how you convert here to here, right, is asking how many SD, right? So if you convert here to here, it's just this times of SD, right? So this is, we know already. So nothing is new here. So that's why it established M is exactly this formula. So that's done. We'll go into more detail in the slide, but that's the idea. So how much you should go left and right is Z alpha over 2 times sigma over root n. So this is called the margin of error. You may be worried about the math declaration. I just try to show you, but it is technical. So again, same as what we said. If you trust me or trust the textbook, this is the answer. But I do recommend you try to understand what's going on. Otherwise, you just memorize it is not good for your learning. I hope I convince you this is true. Okay. So let's go to a slide and then you go slowly to make sure they understand. So mathematically, what we want is the following. We want this, right? This is same as saying that X bar plus M and X bar minus M, you include the mu, right? So that's what I said, is high probability. And we'll show this is true. That's what I just showed in the whiteboard, right? So let's see the little bit math here. So before the math is just what we show a little bit math. The little math is only cost you 2-page, but I guess none of you want to go over that. So that's why I don't want to bother you. This is the formula. Okay. And this is called the marginal error. It's the second part, right? It's just M is go left and right by this amount, this amount. And 2 times of this is called the width. And the lowest is called LCL, the largest UCL. So basically it's like this, right? Your X bar, you go left by Z alpha over 2, sigma over root n, right? And this is known as marginal error. Okay. And this guy is this is the higher value called UCL. The lower value is called LCL. And this whole thing is called the width. Okay. So I think I already justify why this is true. Okay. So now instead of telling the proof, I guess none of you would be interested in the math. I mean, of course, I already explained why this is true based on the graph. The graph is basically the proof, but I don't see any of you are interested in the proof at all, which makes sense, right? But if you really want to ask me true, I can show you again. But instead, I want to show you how you operationalize the math here. So basically, if you remember the formula which you will bring to your exam theater, you want to set confidence interval, okay, with known population variance, which is we know sigma. So the formula is like this, which is copying from the previous slide. All right, this is the formula. Okay. So what you're going to do is to plug in all the numbers there. First, we know this sigma is 4. So this guy is 4. Okay. The question also said we have got a sample with sample size 64. So this means this n is 64. And the sample mean is 3, which is just 3. Okay. So to remind you that if we ask you what's the best guess for the population mean, will be 3, right? But we really want to have a better guess on the 3 instead of 3. We want to know what are the other possibility, right? Because 3 is, you will have 0 chances exactly 3, right? So how can we get further? So we want 95 confidence level. Okay. Is this formula. Just to remind you why this is confidence. Because you have probability before you do the sample. Once you do the sample, you collect data, there's no probability anymore, right? Because you fix it. It's either the interval contain the mu or it doesn't, right? So that's why we have a confidence on this process, okay? Which means that if we collect 100 of those, 95 of them will include. Although we don't know which 5 is not, which 95 is. So, but we have confidence on our procedure. So that's why we call confidence interval, not probability interval. So how to get this z alpha 2? Remember, this is just this, right? This is 0 here. This is z. Alpha over 2 means this is alpha 2. Okay. And alpha here is 5%, right? Because it's 1 minus alpha, right? Alpha is 5%. So alpha over 2 is 0.025. Okay. And that means that the left-hand side is what? Is 90 or 0.975, right? So from probability to number is called the inverse, right? So that's why Excel function, how to get this one, is norm s dot norm dot s dot inverse 0.975. Okay. So that would be the answer. And this, no surprise to you, is 1.96, right? Because that come from the 2 sigma rule, right? 95 is 2 sigma, right? So once you plug in all the number there, right? Now you have all the number, just using calculator, then you show you the mean is between 2 and 4, right? So your best guess is 3, and if you are allowed to guess more, it will be you likely between 2 and 4, right? If it is below 2 or beyond 4, you'll be very surprised, right? Because this is what you get from the data. Is that clear? So we operationalize and how we apply that formula. And that is very important because you'll be using it for a lot of cases. We require to calculate the interval, right? Because we are not happy with just 3, right? Because 3 is just one number, and this number is actually the mu have probably 0, right? That's very unlikely that this is true, right? So we want to see how good our guess is, right? By knowing sigma square, which of course most of the time we don't know, but suppose we know, then we can give a range that highly likely that it will include our true mu, right? And you can easily see that when n goes very large, okay? And this range we're getting strengths very small, so you are fairly sure that can guess what is the mu, right? So that is what we have. Is that clear? So you do this example anyway. You do this in assignment. So so when you know this population variance, you will use this formula. Okay. And here we don't right need to use normality assumption because central limit theorem would already enable us to answer this question. Okay. Now, once we're done, the next one would be to see what do I actually mean by confidence interval, right? Just graphically. So you may end up here and draw interval like this. This will include 0. You're here, you also include 0. Here, you include 0. But this case is far away, doesn't? This case, yes. So that means that one must alpha fraction of your interval to be drawn is including the mu. Okay, so that's the idea. So I think I explained already what the tricky definition. That's why we say confidence interval, but not probability interval. So next would be if we don't know the population variance, which is the case in general. So we have to use S square, right? And we learned from the last class, we have to make assumption on normality. Okay. In that case, we will have this formula, right? As long as we are willing to assume the underlying data is follow normal, which you can check whether right or wrong, that will follow a t distribution, right? Once we see that our formula for interval estimate is same, right? Because it was z over 2, but now it's t, okay? So in that case, it will be this formula, okay? Is t n minus 1 comma alpha over 2 is not set, right? It's t. So because of you don't know the population variance and you replace it with the sample version, then if you assume normality, then you can use t. Okay. But do know that t has many tables, not just one. It looks like a bell curve, fortunately, but there are many tables, and the tables depends on the sample size. And we will pick the table, which is the sample size minus 1. Okay. So let me do it again for example. So here is we have unknown variance. And unknown variance, that means that we will have a what we call normality assumption. Okay. And we have a sample size 20, sample mean 3, sample standard deviation 12. So this is very normal, right? So we don't know anything about this population, what it looks like, okay? The only assumption we make is normality. The other thing is just coming from data, right? So we don't know anything about population. There's zero knowledge about population, except we make assumption that it's normal. So that's very common case when you handle data, right? You don't know anything about population, right? Otherwise, we're done, right? So in that case, if you are only to guess mu, right? So X bar is already done, right? So this is already done deal. If you only ask to give you a one particular point, there's point estimate, I will just free, right? But if you want to do further, you want to give, say, 95 confidence level, that means you follow the formula X bar plus minus T n minus 1 alpha over 2 S over root n. Right? So that is the formula that we'll be using because we don't know the population variance. Right? So first, X bar is 3, so this is good. So this is we know already. Okay. S is also known from the data. 12, right? This is something from your data, right? And N, you know it already. It's 20. Okay. So what left here is this guy, right? And remember, this guy is actually a bell curve, right? But this is the bell with a fatter tail, right? You compare normal, it's just like it's factor, right? So you say, if normal is something like this, the normal is something like this. The normal is something like this, right? The normal, right? This is normal, and T will be the blue one, okay? And this is T n minus 1, right? N is 20, so it's T19, right? Remember, T has many table. We pick up the table, it's the 19th table. How to decide which table we look at is n minus 1, so look at the sample size. You take away 1 from it, it's the 19th table. Okay? And why is not 20, but just the way they name it, right? Just, I mean, you understand why it's 19. It's easiest just to fix idea. Now the center is 0. Okay? And what we have is alpha over 2, right? So it means that the tail is alpha over 2. Okay? What's alpha? Is 1 minus alpha is 95%. Okay? So it means alpha is 0.05, right? Because 1 minus alpha is 95%, right? So alpha is 5%, which is 0.05. And alpha over 2 is 0.025, right? And that means if the right-hand side is 0.025, what is the left-hand side? The left-hand side will be 0.975, right? And this is T table, 0.975. It's just T dot inverse 0.975 19. Okay, and this gives you number 2. Okay, let me show you in Excel. T dot inverse. So you can see I use the formula T dot inverse 0.975 19. Okay, give us 2.09. It's a number that I have in the slide, right? So this is what I have here. So that's how you get the 2.39 here. Something is wrong. So once you know this number, plug that in, and everything is there, right? So now you know this is 2.09. Okay, and you just plug all this number in, then end up is much larger. You will see the average gas is 3, but the lowest case can be negative 2.6. The best case is 8.6. So that is something a little bit much bigger range than we would expect. Okay, so it can be very large, can be very small. But of course, because we only use a very small sample, you can notice that when you increase the sample to 200 or 300, then your data will be much more accurate. Your guess will be much better. This means that it's a really lousy guess because the sample size is small. Okay, so only because of you have a small sample. When you have large sample, you don't have this problem. Is that clear? Okay. Now we're clear. So what we are doing is we want to extend our knowledge of x bar equal to 3, okay, to a range of values, okay, and this range of value would have high probability to include mu, okay. The formula is just given from this one, okay. Then you can just plug the numbers in, then you are done. But why this is true is because this x bar would follow a t distribution, right? X bar will be x bar minus mu over s over root n, follow a t distribution. Okay, so that's why we want to calculate what is this area, this number, so that this is a distance, this is the marginal error, left and right, right? How big should we go left and right? And this is the number you should go left and right. Okay. And how much left and right is very simple because it's proportional to the sample standard deviation, right? If your sample standard deviation is very large, then your estimate is not very accurate, right? When your n is very big, then actually you get a lot of data from a sample, and your sample mean is actually fairly accurate. Okay. Do remember that this ys over n, what's this? This is SD of x bar, right? Remember, this is SD of x bar, right? So basically, just go left and right by the SD, right? And you guess how many SD you should go? Basically, it's 2 SD, right? But it's not exactly 2 SD because this is not normal. It's not 1.96. It really because of n is not big enough, so the tail is fatter. So instead of 1.96, you go by 2.09. So that's the reason why we have this. Okay. I can see that you may not perfectly get it, but were we not on Friday, we will try to review this again to see if you still have a problem. Okay, so I guess we end here. We'll see you on Friday. Stay safe, stay cold, stay dry, and stay warm. I see you on Friday.